Hello everyone, I hope you are doing well. Welcome to Login Science. Today's video will be on Doppler effect and this is our lesson 1 of 2. Before I can start, I want to remind you to subscribe to your channel and activate the notification bell so that you can be notified every time I post new content for you. Down below is my name and the email address at which you can contact us. If you have any question or anything that you'd like to let us know, feel free to use the email address down below. Okay, let's start with our lesson of today. Okay, let's start with the Doppler effect. So this is the Doppler effect with sound. It is our lesson 1 of 2. So lesson 2 of 2 will be the Doppler effect with light. Okay, for now, we are looking at the Doppler effect with sound, which is our lesson 1 of 2. Let's start with the introduction. What is a sound? A sound is a vibration that propagates as an audible wave of pressure through a medium. So as I speak, you can hear my voice because vibration in my voice box. This vibration produces an audible wave which is propagating in all directions. So we say a sound is a vibration that propagates as an audible wave of pressure through a medium. So the medium can be air, water, or a solid. And vibrations cause waves, and waves too cause vibration. So when there's a vibration, the vibration will cause the wave, and the wave too will cause vibration. There are two kinds of waves, transverse waves and longitudinal waves. The transverse waves are waves in which the disturbance occurs perpendicular to the direction of travel of the waves. So you have the disturbance occurring perpendicular to the direction of travel of the waves, and this will create transverse waves. For example, you have light waves, radio waves, microwaves, X-rays. So you'll find transverse waves in light waves, radio waves, microwaves, and X-rays, and so on. Longitudinal waves are waves in which the disturbance occurs parallel to the direction of travel of the waves. So in this one, the disturbance occurs parallel to the direction of travel of the waves. For example, we have sound waves. So in sound waves, you'll find longitudinal waves. Okay, let's see at some drawings where we can illustrate how the sound waves are produced. The first scenario is that of a stationary source and a stationary observer. Okay, you can see you have your source, which is the ambulance, and this ambulance has got a siren, which is emitting a sound. You also have a stationary observer, so both the source and the observer are stationary. From the siren of the ambulance, sound is being emitted, and you have these waves which are being propagated in all directions, and the wave front are formed. You have the observer, which is stationary. The observer is perceiving the sound from the siren of this ambulance. Okay, and here down below you can represent the wave front as a periodic wave. You have there the periodic wave. It can be represented like this, and you have this is your wavelength. From there to there, the distance is known as a wavelength. We're going to see that in more details. And what is happening here when you have the source and the observer stationary? In this case, when you have the source and the observer stationary, so FL, which is the frequency perceived by the listener or the observer, will be equal to the frequency emitted by the source. And now let's look at the second scenario. The second scenario is when you have a source moving toward a stationary observer. Let's see the drawing. You have now the ambulance is moving toward the observer. You can see. So what is happening here? As the ambulance is moving toward this stationary observer, the observer will perceive a higher frequency. It seems as if the volume of the sound from the siren of the ambulance is increasing as the ambulance is approaching the observer. But what is happening is that the observer is perceiving a higher pitch from the sound emitted by the ambulance, or we can say is perceiving a higher frequency. So a short wavelength implies a higher frequency, and a longer wavelength implies a smaller frequency. This is common sense. I don't know if you have experienced that before. When there is an ambulance or a police car with a siren producing sound, when it's getting closer to you, you will think as if the volume of the sound from the siren is increasing. But what normally happens is that the pitch or the frequency you are perceiving will be higher than the frequency produced from the police car or from the ambulance. And you can see in this case what is happening in front of the ambulance here, where the waves are compressed. You will have a short wavelength. This is represented by this periodic wave down here. You can see as compared to the previous one from here, this is now very short, but you have a higher frequency here in front of the ambulance. So this observer now is perceiving a higher frequency when the ambulance is moving toward him. So the Doppler effect will take effect when there is relative motion between the source and the observer. When there is no motion, as in the first scenario, FL is equal to Fs. And in this one, when the ambulance is moving toward the observer, now the perceived frequency by the listener is greater than the frequency emitted by the source. You can see this is greater than. So FL is greater than Fs. Let's see the next scenario. Now in the next scenario is when you have the source moving away from a stationary observer. Let's see the drawing. Now the ambulance is moving away. You can see you have the observer still stationary, but the ambulance is moving away. Now you can see the compression now is happening in front of the ambulance, but you have the observer at the back of the ambulance. The ambulance is moving away from the observer, and common sense tells you that this observer will perceive a lower frequency as compared to the frequency emitted by the source being the ambulance. Can you see at the back of the ambulance, the sound waves are elongated, and in front of the ambulance, the sound waves are compressed. Can you see that? So when you have sound waves compressed, this will give you a short wavelength, but a higher frequency. But since the ambulance is moving away, the observer will perceive a lower frequency. You can see the observer is at the back of the ambulance, and you can see the sound waves at the back of the ambulance are elongated, meaning you have a long wavelength but a lower frequency. This is common sense. When the ambulance is getting away from this observer, the observer will perceive a lower frequency or a lower pitch. It seems as if the volume of the sound from the siren of the ambulance is decreasing, but what normally happens is that the observer is perceiving a lower frequency or a lower pitch as the ambulance is moving away. And now you can see when you represent the sound wave down here, you can see the wavelength is longer than the one in the previous scenario where it's short. You can see now the wavelength is long. Okay, what is happening now? FL, the frequency perceived by the listener, is less than the frequency emitted by the source. This is what is happening here. And this is common sense. The ambulance is moving away, so the frequency perceived by the listener will be less than the frequency emitted by the source. Common sense. To add, you expect the observer to perceive a higher frequency. When it is away, you expect the observer to perceive a lower frequency as compared to the frequency emitted by the source, right? Okay, now if we can represent the sound waves, you'll see we'll get something like this, which is a periodic wave. This is some kind of sine or cosine graph. You can see this is what we have. You can see from that point to that point, the distance is known as the wavelength. Okay, we are going to see that in details. You have the top part, which is known as a crest, S there in bracket for many. So this is a crest, and this is another crest, and this is another crest. So the top turning point are known as crest. Can you see? The lower ones, they are known as trough. So troughs for many or plural. So this is a trough, and this is another trough, and this is another trough. So this position, the line there, is known as the undisturbed position. And the distance from the undisturbed position to the crest is known as the amplitude. Or you can say the distance from the undisturbed position to the troughs is also the amplitude. Okay, you have A there for amplitude, and you have A there for amplitude. I hope it's clear there. And if you want to see where are your crest and your troughs on the sound wave represented in any of these scenario, your black lines will represent your crest, and the empty spaces here, the white spaces where there is no line, will be your troughs. Okay, the lines represent your crest, and the white space or the empty space where there is no line will be your troughs. Okay, let's continue. And now let's look at some formula. The first formula is this one. Okay, what are the letters in the formula? You have V, which is the speed of sound waves. It can be given as 340 meters per second. So depending on the value given, use the value that you'll be given. Or sometimes they can ask you to calculate the speed of sound waves. F is the frequency of sound waves expressed in hertz. So these are the units for frequency. The hertz are also equal to 1 over second, or you can say per second. But these units, the hertz, are the one used most of the time. And this is lambda, which is the 11th letter of the Greek alphabet. We use this to represent the wavelength of sound waves. The unit for the wavelengths are the meters. The next formula is this one. F is equal to 1 over T. F is still the frequency of sound waves, and we are going to see what T is. You can also change this formula into this one. T equal to 1 over F. So from F equal to 1 over T, you can also write T is equal to 1 over F. So we said that F is the frequency of sound waves. And what is T? T is the period of sound waves. We are going to see that. So the units for the period of sound waves are the second. This is second. To understand what period is, the period is the time it took one complete wave to complete. So you have that top part and the lower part. The time it took for this complete wave to complete. That is the period. So this is a complete wave when you have the top part and the lower part. You can also have a complete wave from a crest to the next crest, or from a trough to the next trough. That is also a complete wave. And the time it takes to complete a complete wave will be the period, which is expressed in second. The next slide, we still continue with the formula. And now you have this formula, which will be used most of the times. So what are the letters in this formula? You have FL, which is the frequency perceived by the observer or the listener. FL is the frequency perceived by the observer. Fs is the frequency emitted by the source. VL is the speed of the observer or the listener. So if the observer is stationary, you know that VL will be equal to 0. Vs is the speed of the source, and V is the speed of the sound waves. Normally, this is given, or they can also ask you to calculate it. Now, we are going to see how to choose the signs in the Doppler effect formula. So in this formula, when to put plus or minus at the top and when to put plus or minus at the bottom. We are going to see that. Let's see as we move on. To choose the signs plus or minus in the Doppler effect formula, you will need to identify first the situation you are given. You have to identify first the situations so that you can decide on your sign at the top and at the bottom. You'll come across two situations, the toward situation and the away situation. So two situations, toward situation and away situation. Toward situation is when the source is moving toward a stationary observer, or when the observer is moving toward a stationary source, or when both the source and observer are moving toward each other. So you should identify first the situation you are dealing with, if it's toward or away. And now, in away situation is when the source is moving away from a stationary observer, or the observer is moving away from a stationary source, or both the source and the observer are moving away from each other, right? You can go back and read over so that you can understand the English. This is simple. You must be able to identify when it is away situation and when it is toward situation. Okay, we are going to use the knowledge of fractions to help us identify the signs here. Let's see. For example, from primary, you see when you have this type of fraction where the numerator is bigger than the denominator. You can see this is your numerator at the top and the denominator at the bottom. And the answer for this fraction, 4 over 2, is equal to 2. And this is known as an improper fraction. What is happening here? The answer is always greater than 1. Whenever you have a numerator bigger than the denominator, the answer will always be greater than 1. Always. When the numerator is bigger than the denominator, the answer will always be greater than 1. You don't need to be good at mathematics for you to understand this. This is primary stuff. You must understand your fraction. Always, when the top part is bigger than the bottom part, the answer will always be greater than 1. What I want you to pay attention to is the word greater than. I want you to keep this in mind. I'm going to show you how this can help you. For now, keep the word greater than in your mind. And the next fraction is this one, which is known as a proper fraction. So for a proper fraction, you have the denominator greater than the numerator. You can see the numerator is less than the denominator. And when you have such a fraction, the answer will always be less than 1. You can see you have 0.75. This is less than 1. Always, when the bottom part is bigger than the top part, the answer will always be less than 1. I want you to keep this in mind. Okay, now for toward situation, when you have your formula there, how will you choose the signs? When it's toward, you expect the perceived frequency by the observer or the listener to be greater common sense tells you when it is toward, the perceived frequency must be greater than the frequency emitted by the source. And how will you achieve this? Look at this part as your fraction. So to achieve a perceived frequency that is greater than the frequency emitted by the source, you have to get the top part greater than the bottom part. Let me say it again. To achieve a perceived frequency that is greater than the frequency emitted by the source, you must get the top part bigger than the bottom part, like this fraction. And you're gonna achieve this top part bigger than the bottom part by having addition there. So you're making the top part bigger when you have addition, and you are making this small by having subtraction there. When it's like this, you are going to achieve FL greater than Fs. Okay, now the next situation is the away situation. How will you choose your sign? When it is away, common sense tells you that FL will be less than Fs. FL, the perceived frequency by the listener or the observer, must be less than the frequency emitted by the source. So for you to achieve the perceived frequency less than the frequency emitted by the source, what you should do is to look at this fraction here. To achieve something that is less than, you make the bottom part bigger than the top part. So you're gonna make this bottom part bigger than the top part. How will you achieve that? So you'll achieve a bigger number at the bottom by using addition there, and a smaller number at the top by using subtraction there. Okay, and this will give you FL lesser than Fs. Okay, next we look at an example. Okay, this is the example. Let's read the question. What is the frequency heard by a person driving at 15 meters per second toward a factory whistle that is blowing at a frequency of 800 Hz? Assume that the speed of sound in air is 340 meters per second. You can see you are given the speed of sound to be 340 meters per second. Let's solve the question. Start with solutions. So the question says, find FL. When you read the question is saying, what is the frequency heard by a person? So this is what FL is, the perceived frequency by the listener or the observer. So the person is the listener or the observer. And we are told that VL, which is the speed of the listener or the observer, is equal to 15 meters per second. You can see the question says the person is driving. So the person is in a car that is moving at 15 meters per second. And the next information is Vs. You can see Vs is equal to 0 meters per second. Can you see that? You can see Vs is the speed of the source, and the source is the factory. You can see the factory is not moving. The factory is what? Stationary, at rest. It's not moving. So Vs is equal to 0. The whistle is on the factory. The factory is the source. So Vs is equal to 0. And the frequency of the sound from the whistle, Fs, is equal to 800 Hz. You can see Fs is equal to 800 Hz. And you are given V, the speed of sound in air, is 340 meters per second. Now we need to calculate what? FL, the perceived frequency by the listener or the observer. So we'll need this formula to find FL. And which situation is this? When you check, it says toward. Can you see that? So when it is toward, you will expect this FL to be greater than Fs, common sense. And to get FL greater than Fs, you are going to have a bigger numerator over a smaller denominator. so that FL will be greater than FS. So how are you going to get a bigger numerator? You must have addition there and subtraction there. In this case, you are going to achieve FL greater than FS, right? And now you plug in the values. You have V there. V is 340 plus VL. VL is 15 meters per second. 340 minus VS. VS is 0 times 800. Okay, and you just use your calculator and see what the answer is. So this is what we have. You have 340 there plus 15 over 340. So 340 minus 0 is 340. So times 800. And what is the answer? You press this to get the answer in decimal. So the answer is 835.29. Let's get the answer to 2 decimal place. Okay. So this is the answer, 835.29 Hz. This is your FL, the frequency perceived by the listener. Can you see, does it make sense? 835.29 as FL, and FS was 800. Can you see? FS was 800, and the perceived frequency is greater than the frequency emitted by the source. Since it is toward situation, this makes sense. Okay. Now let's look at the terminology. I'm going to need this to explain some of the terminology. The first one is the Doppler effect is the change in frequency of the sound detected by a listener because the source and the listener have different velocities relative to the medium of propagation. Can you read that again and try to understand what the statement is? So if you are asked to state the Doppler effect, this is what they require you to give. The Doppler effect is the change in frequency of the sound detected by a listener. So the sound is detected by the listener because the source and the listener have different velocities relative to the medium of propagation. Okay, if you find the first one complicated, you can give the second one. So the second one says the Doppler effect is an apparent change in observed frequency as a result of the relative motion between a source and a listener. The next terminology is this one. The amplitude of a wave motion is the maximum displacement of the particles from their equilibrium position. So you have the amplitude. This is the equilibrium position or the rest position, this one, known as the undisturbed position. So from there to the crest, as we've seen it previously, or from there to the trough below. So you have your trough below and your crest at the top. So from the undisturbed position to the crest, or from the undisturbed position to the trough, the height or the distance is known as the amplitude. And the amplitude determines the volume of a sound waves. Okay, the next terminology, the wavelength of a wave is the distance between two consecutive points in the wave which are in phase, or it is the distance between two successive crests, or the distance between two successive troughs. So this is your wavelength. Can you see, from that point to that point, this distance is the wavelength. Or you can say from your trough, this one, to the next one, this point, the turning point, the lower point, this one to the next one, that distance is known as the wavelength. Or you can take the top part, your crest, from that point, the turning point there, to the next one, the distance is also the wavelength. So the next terminology, the frequency of a wave motion is the number of complete waves passing a specific point per second, and the frequency is measured in hertz. So the number of complete waves, let's say you have this part and this one, this is a complete wave. You have that part and this one, this is a complete wave. You have this part and this is a complete wave. So the number of complete waves per second will be your frequency. So let's say in 1 second you have 10 complete waves. The frequency will be 10 Hz. Or if you have 50 complete waves in 1 second, then the frequency will be 50 Hz. And the frequency of a sound wave determines its pitch. So a higher frequency means a higher pitch. The frequency of a wave also determines the energy of the wave. So the higher the frequency, the higher the energy. And what is the period? The period of a wave motion is the time taken for one complete wave to pass a fixed point. So the time it took this, can you see that? This complete wave to complete. That is your period. And lastly, we look at applications of the Doppler effect with ultrasound waves. We are not going to go into more details when talking about ultrasound waves. So we said the knowledge of ultrasound waves is used in medicine to do things like measuring the speed of blood flow with the help of a Doppler flow meter. And the knowledge of ultrasound waves is also used to diagnose the body, to detect tumors in the liver, kidney, brain, and pancreas. Sound whose frequency lies below 20 Hz or above 20 kHz cannot be heard by the human ear. So below 20 Hz or above 20 kHz, such sound cannot be heard by the human ear. And sound waves with frequencies below 20 Hz are said to be infrasonic. So below 20 Hz, they are said to be infrasonic, while those with frequencies above 20 kHz are referred to as ultrasonic. Some birds use ultrasonic sound waves for locating prey and for navigating. So you have the image of the bird there. Rhinoceroses use infrasonic sound waves to call to one another, and you have the image of rhinoceroses there. Okay, this is all for lesson 1 of 2 on Doppler effect. If you haven't subscribed to your channel, don't forget to subscribe and activate the notification bell so that you can be notified every time I post new content for you. If you want the note of this video in PDF format, please do check the description of this video. You'll find the note in PDF format. This is all for today. Take care and see you next time.